Okay, time to think about polar equations again. Holy Moses. Ooh, that's some fuerte café. Café fuerte. I don't know what this drawing is. I apologize. Polar equations, you remember them? Oh, yes, you do. You've got a radius, depends on some angle theta. I haven't looked at these in months, so we're going to be thinking through them together. So r equals 3 sine 2 theta. All right, well, one thing that might help me is to think about y equals 3 sine 2 theta. I mean, sine 2x. So in other words, the Cartesian version of this same thing, because that can sort of help me when I'm thinking about sketching this. So y equals 3 sine 2x. I know this thing has an amplitude of 3, right? I know that it has a period of pi, right? Because that would be 2 pi over 2. So the graph of this little beast does this, I think, and it goes up to 3, it goes down to -3, and this is pi, and that's pi halves, and this is 3 pi halves, and that's 2 pi. So this is 3 sine of 2x. That's the Cartesian version of that, that equation. So this can help me, right? Because now the y values on this are the radius values, and the x values are the theta values. So remember, we're going to be graphing this thing on a plane where r is distance from the origin, right? And theta is measured from the x-axis being spun around. So I know when theta equals 0, r equals 0. I know but by the time I get back to pi halves, I'm at 0 again. So what happens in between? Well, at pi fourths angle, I'm all the way out to 3. Dun, dun, dun. I actually love polar equations. So I should be out here at 3, right? And I'm increasing in between. So this is as my angles increase, right? This should be coming out. Then as my angles continue to increase, they're coming back down. So it should come back down like that. Okay? Now, what's happening between pi halves and pi? Similar, but as I'm coming between pi halves and pi, I have negative radii, right? Yes, because my y values are negative, that means my radii are negative. And remember, negative radii mean instead of it coming out like this, I'm going to be coming out the other direction because all my radii are negative, right? Right here at 3 pi fourths, I'm actually going -3. So positive 3 pi fourths is here, but -3 pi fourths is back here. So it's going to come out like this. So this right here, this point in polar coordinates is pi fourths comma 3. This point is 3 pi fourths comma -3, because I'm going at this angle, but in the opposite direction. So I'm tracing it like this, okay? And then in between, it's going to be positive between pi and 3 pi halves. So positive again here, it's going to do that. Come down to, what is that? That's 5 pi fourths, comma 3. That's this point right here. And then it's going to come up like this. So these are all negative again. My angles are sweeping out this way, but they're doing this. So they're coming in the negative direction. So this right here is 7 pi fourths, comma -3. So if we wanted to think about tracing this, it goes here, positive radii, back to 0, then negative radii, right? Negative radii as my angles come around like this, then positive radii again as my angles come around like this, then negative radii again as my angles come around like this. And remember, negative meaning you're going in the opposite direction from the angle instead of the positive direction. So this is a rose curve, yay! And it has 4 petals of length 3. Fun. All right, so let's think about 4 cosine of 3 theta. So again, I'm going to help myself out by saying y equals 4 cosine of 3x. So this has a period of 2 pi thirds, daggone it, and it's got an amplitude of 4. So what does that look like? Well, it starts at 4, it comes down like this, and then all the way back up, and this is 2 pi thirds, which means this is pi thirds, which means that's pi sixths, which means this is 1, 2, 3 pi sixths, which is pi halves. So that gives me quite a bit of information there. Okay, you might not be as good at this as I am, or you might be better, I'm not sure, but it's really helpful to be able to sketch these in Cartesian coordinates and then translate them to polar. Okay, so let's see what goes on here. So I know at angle 0, right there, I have a radius of 4. 1, 2, 3, 4, so it needs to start there. I know by the time my angle gets to pi sixths, which is right here, I need this thing to have come down to 0, right? Because my radius is going all the way down to 0 by the time I get to pi 6. Holy heck. By the time I get to pi thirds, which is here, I know I have to be down at negative 4. So that means this would be pi thirds 4, but I want pi thirds negative 4. That's here. So this thing does this and then comes down around like that. By the time I get back to pi halves, which is this angle right here, I'm back down to 0, so it should be right there. Goodness gracious, it's not the easiest thing to sketch. By the time I get to 2 pi thirds, which by the way is right here, I'm all the way back up to 4 again, so it's coming up here. So that is one Cartesian period of the graph. I started at 4, then I came down to 0. Yeah. Then I kept going around with positive angles, but that means a negative radius. There's pi thirds. So this point right here is pi thirds, comma, negative 4. So pi thirds, comma, negative 4. And I came back to 0 by the time I got to pi halves, and I continued up here. Now if I continue the graph, it's going to repeat. It's going to do the same thing. So let's see here. I should be back up at the top by the time I get to 4 pi thirds, right? And then 6 pi thirds is going to be my third period. So this thing is going to come back down. Let's see, each one of these is after pi 6. This is 4, so this should be 5 pi 6, I think. 4 pi 6, 5 pi 6. 5 pi 6 is right here. I should, by the time I'm at that angle, I should be back to 0, so it's coming down like that. Then it's going negative between 5 pi 6 and 6 pi 6, which is pi. So by the time I get to pi, I should be back there. So note, that is like not even, it's like a weird, like not even, it's like a period and a half of this thing, and I've done this entire curve. And then I'm going to repeat over it. So I do all of this in pi, okay? Twice in 2 pi. So I start here, and by the time I get to pi, I'm already back to this beginning, and then I do it again by the time I get back to 2 pi. So it's actually happening twice in 2 pi. But again, what is this? This is a rose curve with 3 petals, and they have length 4. So you notice that if this is multiplied by an odd number, that's the number of petals you have. I think this is true. So we ended up with 3 petals because we're going over the same thing twice. So it's almost like you have 6 petals, but they're all on top of each other. Here, when you multiply by an even number, you see all of the petals because you're not going over the petals again. So this one, from 0 to 2 pi, we're actually going over these petals twice. So there are 6 petals, but they're like right on top of each other. And here, you see all 4 petals. So that's the difference between multiplying by 3 and multiplying by 2. So what we can see here is when you change this period by multiplying by 2 or 3, you get some sort of rose curve. Oh my goodness. Okay, so how about this right here? Well, again, I think it's good to look at y equals 1 plus 2 cosine x. So what happens here? Well, that shifts your center line to y equals 1. It shifts everything up 1, and then your amplitude is 2. So here is y equals 1. That's where this thing is going to be centered. Then I need to go 2 above and 2 below. So in Cartesian, it should be bouncing between 3 and negative 1. It's cosine, so it starts at the max, completes 1 full rotation by the time I get to 2 pi, because I haven't changed the period, it's 1x. So then this should be pi, and this should be pi halves, and this should be 3 pi halves. Okay, so little bit interesting here. So now let's convert it to polar. So I started with a radius of 3. 1, 2, 3. So at an angle of 0, my radius is at 3. By the time I get to pi halves, which is up here, my radius is now at 1. So that angle is 1, and it's decreasing the whole time. So my angles are doing this. My radius is coming down and decreasing, like so. By the time I get to pi, which is this direction, my radius is -1. What? So there's some point in between here where I actually cross 0. So as my angles are increasing here, I'm going to come around, I'm going to cross 0, and I'm going to cross 0. Let me think how this works. I'm going to cross 0 right there, and then I'm going to end up with a negative radius. So positive radii here, but then negative radii here. So for the angles in between that spot, here to here, I have all negative radii, which is creating that little thing there. If they were positive, it would look like this, but they're not. They're negative, so it makes them go negative back there. Then it basically does the same thing. It's got negative when you're coming around here, so negative radii like that, then it crosses 0 again right there. Then it becomes positive radii again, so in the direction of the angle, and then it comes back around like that. So that's a little bit strange to think about, but that's what happens. And this we call a limaçon, or something. I don't know how to pronounce that, but I think this means snail in French. So those of you who are taking French can criticize my pronunciation and criticize my translation. I dare you and defy you. Kind of looks like a snail. Interesting. Okay, so notice when you add that 1 on there, you get some weird thing. So how about this beast right here? So again, let's look at the Cartesian. Y equals 3 plus 2 cosine x. Okay, center line of 3, 1, 2, 3, dot, 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 dot. And it has an amplitude of 2, so it should go up to 5 and down to 1. And otherwise it looks the same. It repeats every 2 pi, and this is pi. So one thing you'll notice about the Cartesian graph here is that it is always positive, whereas this one went negative. So when you have that weird negative thing, that's where you're getting this loop inside, right? Where this little thing is corresponding to these angles, but they're all flipped this way. Your radii are negative, so that's why the curve is going out over here. This one is always going to be positive. All right, so we started with a radius of 5. 1, 2, 3, 4, 5 right there. Then by the time we got to pi halves, which is the angle right here, our radii have been decreasing until we got to 3. 1, 2, 3. So it goes like that. Then they continue decreasing until we get to the angle pi, and we get to a radius of simply 1. So it's coming down like that. Then the radii increase till we get to 3 by the time we're here. 1, 2, 3. So they're going to increase. This probably is going to go more something like this. And then it's going to come around like that. And then they're going to continue increasing until we get back to a radius of 5. So this we call a cardioid. Cardioid. That's not how you spell cardioid. Cardioid. Because it looks like this. But it's also a type of limaçon, right? It's a type of limaçon that doesn't have that extra little curve in there, but specifically we call it a cardioid. So hopefully this should give you a good sense of a reminder of how to sketch polar curves. They can get pretty confusing, and we want to be really clear about things like, oh, this is not the angle 4 pi thirds. That's the angle pi thirds with a negative radius. So we have to think pretty carefully, and I would suggest that being able to sketch your Cartesian graphs is pretty useful. So in the next video, what we want to do is start thinking about, well, how do we find the lengths of these curves, and how do we find the areas of petals and cardioids?